everybody, welcome back. Mr. G here again. Today is the next series in the Tech 101 lectures for electric circuits. This is power in resistors. So a new topic, we're going to be looking at power in resistors. So what is power in resistors? Well, what is power? So basically, if you remember from any kind of physics discussion, there's a law of energy conversion. And that law says that any kind of energy cannot be created or destroyed, but only changed in form. So, energy cannot be created nor destroyed, but only changed in form. So we can change energy from this black wiggly mass into a red circly mass. So, we have energy can change form. We cannot create nor destroy energy, but we can change its form. So how does that actually translate into electronics, specifically resistors? Well, as we hook up a resistor to a power supply, so basically a potential energy source, we have current that is going to be created, and that current will flow through the resistance. Now, the energy from the source changes as it goes through the resistor. So the energy, if I was here, had 10 volts. So the potential across that resistor would be our 10 volts. So that means from one side to the other side, the energy level drops from a potential of 10 to a potential of 0. Where does that energy go? It has to go somewhere, because according to our law, energy can only be changed, can't be created, cannot be destroyed. So the potential energy, the voltage, goes from a potential of 10 volts down to a potential of 0. So that's what 10 volts means. So from one side to the other side, we have a potential difference of 10 volts. Where does that energy go? In resistors, that energy is actually dissipated as heat. The resistors warm up. They dissipate heat, so they give off heat. So the energy transformation goes from this electrical energy that we have, this potential, to heat energy. So the resistor itself gets warm. So the rate at which we get rid of this energy is called power. Power is measured in watts. So this resistor will give off so many watts of heat energy, or power. So power, unit is the watt, Short form, just the W. Capital W. So power in resistors is dissipated as heat. Measured or calculated unit is the watt. So this leads to some issues. Every resistor in every circuit, as it's doing its job, is actually dissipating heat. It's dissipating power. How much power? How do we know when we have too much power? Well, what happens is the resistors heat up. If you do not have a way of getting the heat off of the resistors will actually burn up. So they will become overheated and they will burn. So we need to somehow get rid of the heat. If you think of your engine in your car, the engine in your car heats up. So inside your car, you have explosions that happen. So inside the engine of your car. So here's the engine of your car. You got your spark plugs and the whole bit. Here's the engine of your car. Inside, there are many explosions that are happening, causing the engine to turn over, to run. And that energy, the mechanical energy, is transferred down to the wheels of your car and allow you to travel along. But the heat energy, so the energy from those explosions and the friction, actually is absorbed inside the engine itself. We need to get that heat out of the engine, or else the engine will destroy itself. It will overheat. So we need to get rid of the heat energy. So in your car, we have a radiator. And we have hoses that carry coolant to the radiator. So basically, the coolant is pumped out of the hot engine and flows into the radiator. Then as you drive, you have air blowing onto the radiator. It cools the coolant and puts it back into the engine. And this continues on. What about something like the engine on your lawnmower? Your lawnmower does not have a radiator. Your lawnmower doesn't have any kind of coolant in it to get rid of the heat. It's the same concept though. So we still have an engine for cutting your grass. Something has to spin those blades to cut the grass. But there's no radiator or anything to get rid of the heat. But there are fins, what they call cooling fins, on the side of the engine. What that does, it increases the surface area so that the natural air can cool the engine. It's the same concept as the radiator. We have air flowing through the radiator to cool the liquid. Here we have air flowing past the engine to cool it. The same concept is used in resistors. With a resistor, we use the natural surface area of the resistor, like those fins, to cool the resistor. In your car, the bigger the radiator, the better the cooling. The bigger these fins, the better the cooling. The bigger the resistor, the better the cooling. More surface area to get rid of the excess heat. So, resistors, when they're dissipating power, that heat comes off of the surface area of the resistor. The larger the surface area, the better the cooling. So therefore, resistors that handle more power are typically larger in physical size. So if we had a small resistor, a medium-sized resistor, or a large resistor, they might all be 100 ohms, 100 ohms, 100 ohms. The physical size does not have any effect on the resistance, but it has an effect on how much power that resistor can handle. So how much power that resistor can dissipate. The larger the surface area, the more heat we can get rid of. So with a small resistor, you can get rid of a little bit of heat. Bigger resistor, get rid of more heat. Bigger resistor, you get the idea. More heat. So more power. Less power. So the physical size of the resistor determines how much power we can actually get rid of. There are some common sizes. So there are very, very small resistors, and they can get rid of typically 1/8 of a watt. So this is what we call the ratings. So this is the power rating of resistors. So you can get them in 1/8 watt. You can get them in 1/4 watt. You can get them in 1/2 watt. You can get them in 1 watt, 2 watt, 3 watt, 5 watt, etc., etc., etc. We have resistors in the electric machines lab, and the resistors themselves are about the size of my forearm, physical size. So that's the size of the resistor. And they typically give off somewhere in the neighborhood of 275 watts of power. So what does this all look like? Well, we have small resistors in our kits. They look like this. That is 1/8 of a watt. We have ones that are a little bit bigger. We have 1/4 watt. We have ones not in our kit, but available, and they're about this size. So this is probably a 1 or 2 watt resistor. We also have ones in our kit that look like this. This is what's known as a power resistor. These are a special type of resistor. They are made out of a special material to handle larger amounts of power. This one is 5 watts. So basically it's a ceramic type material. So we have resistors of different physical size. Again, the physical size has nothing to do with the resistance value. This one is 100 ohms. This one is 150 ohms. This one is 27 kiloohms. So the physical size has nothing to do with the actual resistance, but it has to do with the amount of power, the amount of heat it can dissipate. The larger the surface area, the more heat you can actually get rid of. Therefore, that resistor can dissipate more power. So how do we figure that all out? Well, there's what we know as the power formula. The power formula, the basics for the power formula is this. Power is equal to voltage times current. That is the basics for power. So if we look at the generic formula for power, we're looking at voltage times current. That's the generic formula. So that means that if I have a resistor and I know the voltage drop across it and I know the current flowing through it, I can calculate the power. So how much power, how much heat dissipation will that resistor have? Just going to slide this here. There are a few derivative formulas, if you will, based on that one. We know that voltage is equal to I times R. Ohm's law. So if we replace this V with this equivalent, we end up with P is equal to I times R times I. So that works out to be I squared R. We also know from Ohm's law that I is equal to V over R. If we replace this I, we end up with P is equal to V times V divided by R, which works out to be V squared divided by R. So I'm just rearranging formulas and substituting. So what that ends up being is one main formula and two others. Power is equal to I squared R. Power is equal to V squared divided by R. Those are the formulas to calculate power dissipation on a resistor. So, how do we know? Let's say I did a calculation and I had 1 volt and 1 amp of current. It's going to give me power is equal to 1 watt. So that means that the resistor, will dissipate 1 watt of energy. Normally what we do is we build in a safety factor. So we won't put a 1 watt resistor there because we know that it will dissipate 1 watt under normal circumstances. So what we would do is we were picking the size, the physical size of the resistor. We would actually go up 1. So instead of a 1 watt resistor, we might put a 2 watt resistor there. So we know that it's going to get rid of 1 watt of heat, plus we have put in a little bit of a safety. So we've actually oversized it a little bit just in case something was to happen. So when we calculate the power, we get a value. When we're deciding on what physical size resistor to use, we take that value and typically we go to the next one. So we want to make sure we oversize the resistor just to build in some safety. So what we're going to do, I'm going to take this, I'm going to slide this up to this corner up here, and we're going to solve some stuff. So I am going to create a circuit. And let's do this. So here's my circuit. We're going to say V total is 10 volts. We have R1, R2, so this is 1K, 2K. This will be R3 at 3K. This will be R4 at 4K. So we're going to go through the procedure, and what we're going to do is we're going to solve for this circuit. So remember, solving for the circuit, we're calculating all the stuff that we have. So in this particular case, we need to find so VR1, VR2, VR3, VR4. We need to find IR1, IR2, IR3, and IR4. We need to find R total of the circuit, and we need to find I total of the circuit. Now we are going to look at PR1, PR2, PR3, and PR4. So now we have powers to calculate. So up until this point, we've been calculating voltages and currents and so forth. And then we've got now individual powers. But if you notice, we've got individual currents and a total current. We have individual voltages, total voltage. We have individual resistors, total resistance. So if we have individual power, we must also have power total for the circuit. So when it comes to it, we're going to be calculating these values. But we need these values first because we need to be able to plug them into one of those formulas. Okay, so one of these formulas. So I'm going to take this sheet away and just put it there. And we need to solve for this circuit first. So, from our previous lessons, you should be able to identify that this is a series parallel combination circuit. The question becomes, does this simplify to series or does this simplify to parallel? So, in order to do that, we need to be able to identify where I total is. And we have to ask our questions. So, if you remember, we had these questions. Does I total flow through any single resistor? If it does, then this simplifies to a series circuit. If it does not, we move on to this question. Does any resistor have the same voltage as the total? If the answer is yes, then this becomes a parallel circuit. If you answer no and no, then this becomes a little bit more of a complex circuit to solve. So, let's ask our questions. Does IT flow through any single resistor? Well, IT leaves the source, it flows through this resistor, and then it flows through this one. So yes, it flows through resistor 1. It also flows through resistor 2 before it splits up. So that means that this circuit simplifies down to something that is a series circuit. And if you can't remember, there is another video for solving series parallel circuits on the channel, and basically it'll run through these little scenarios for you. So this will solve into a series circuit that looks like this. Where this is R1, this is R2. This resistor is the equivalent of those two. So we have I total, it's going to leave the source. We have V total, which is 10 volts. So we are looking for calculating R total. So R total is these three resistors in series. So R1 plus R2 plus Rx. We know that R1 is 1K, we know that R2 is 2K, but Rx we don't know. So remember, we extract this out of the circuit. Rx is going to be the equivalent of those two. So here's Rx. The equivalent of those two. So 3K and 4K in parallel gives us Rx. So 3K times 4K divided by 3K plus 4K, and that's what gives us Rx. $1.7K. So, the equivalent of these two resistors is this one here at 1.7 kilo. So now our total for the circuit is 1K plus 2K plus 1.7K. 4.7 kilo ohms. I total, according to Ohm's law, is V total divided by R total. 10 divided by 4.7K. 10 divided by 4.7K. 2.13 milliamps. 2.13 milliamps. So, we know that I total flows through this resistor and this resistor. So I total flows through this one and this one. We know what I total is now. So we can say IR1 is 2.13 milliamps. IR2 is 2.13 milliamps. Ohm's law will tell us VR1 is IR1 times R1. IR1, 2.13 milliamps. So 2.13 milliamps times 1K. 2.13 volts. Just separate this a little bit. VR2 is IR2 times R2. And that works out to be 4.26 volts. We know that I total flows through this equivalent resistor. So we can actually say that the voltage across Rx is 1.7K times our I total, which is 2.13 milliamps, 3.621 volts. So across here, 3.621. That is equivalent to these other two resistors. So therefore, the voltage drop across those two resistors is equal to whatever was across that 1.7K. We can prove that all to be true. So we have here 3.621, I believe I said, 4.26, and 2.13 volts. If we add up all of those, 2.13 plus 4.26 plus 3.621 equals 10 volts. 10 volts. Now we can use these voltages here that we got, VR3 and VR4, back into this circuit, and we can calculate the currents. So the voltage was 3.621 divided by 3K, 1.2 milliamps, and divided by 4K. So 3.621 divided by 4K equals 0.91 milliamps. So 0.91 milliamps. I total splits at this point. 0.91 goes that way. 1.2 goes that way. So together, they're going to add up to 1.2 milli plus 0.91 milli. Everything's good. We'll love it when a plan comes together. So now we've solved for all of the values. So I can get rid of this for now because we don't need it anymore. So I now know all of the voltage drops and all of the currents. I know the total resistance and the total current. The total voltage was given. I can now apply any of these formulas and I can calculate the power for each resistor. So how much heat, power dissipation will each one of these resistors be giving off in this circuit? So let's do this formula for the first one. So power of R1 is equal to the voltage across R1 times the current through R1. The voltage across R1 was 2.13 volts. The current through R1 was 2.13 milliamps. Therefore, the power, so 2.13 volts times 2.13 milliamps equals, we have 4.5 milliwatts. 4.5 milliwatts. For the next one, let's just use this formula, I squared R. Again, it doesn't matter which formula we use, they all equate. Since we have all of the values, we can use any formula we want. So I squared, so here we go. And it's very important that you enter in the milliamp part, 2.13 exponent 3 to the negative, milliamps squared times 2K equals 9.0 milliwatts. Let's calculate the last two. Let's use this formula. So PR3, we got 3.621 squared divided by 3K equals 4.37 milliwatts. The next one, we'll do the same way. 3.621 squared divided by 4K. 3.228, let's say 3.28 milliwatts. Now, power total. Those were the individuals, so I use the individual values. Power total, I'm going to use the total values. So let's use this formula. Again, I could use any formula that I want. I'm going to use this one. So this becomes 10 times, so 10 is the total voltage, my total current is 2.13 milliamps. So if I do that, I have 10 times 2.13 milliamps equals 21.3 milliwatts. 21.3 milliwatts. If I calculated it using any of the other formulas, it would all come out to be the same. Now watch this. Power total. Remember, we're talking about heat. So, if I have the heat from this resistor, and the heat from this resistor, and the heat from this resistor, how much do I have? I have the power here, plus the power here, plus the power here. It does not matter whether it is a series circuit or a parallel circuit or a combination, power add up. Because we are just talking about heat. Doesn't matter how these things are oriented, all we're talking about is adding up the heat. Power of the first resistor, in this case, was 4.5 milliwatts. Power of the second one was 9 milliwatts. Power of the third one was 4.37 milliwatts. Power of the fourth one was 3.28 milliwatts. Let's add those up. 4.5 milli plus 9 plus 4.37 plus 3.28 equals 21.15 equals 21.15 milliwatts. So with our error in rounding off and so forth, 21.3, 21.15, those two are virtually equal. Again, the error would be in our rounding of our calculations and so forth. So, basically, each resistor in this circuit will give off some heat. That's the power, what we call power dissipation. We add them all up, and it will give us the total power for the whole circuit, so the total heat of the whole circuit. If we were to pick resistors for these values, the 1/8 of a watt resistor is 125 milliwatts. That resistor would be more than enough to handle any of these powers. So if I was building this circuit, I would pick the 1/8 watt resistor. Why? Because typically the smaller the resistor, the cheaper it is. The bigger the physical size of the resistor, the more expensive. So I want to pick the smallest resistor that's still going to give me a safe power dissipation. So again, remember, the physical size is what gets rid of the heat. Has nothing to do with the resistance value. It just gets rid of the heat. So the bigger the physical resistor gets rid of more heat, but it's also more expensive. So this is power in resistors. I hope this helps. Until next time, everybody stay safe. Take care.